What if the universe we think we understand isn't actually the universe we're living in? That sounds like science fiction, something meant to create drama and mystery. But the unease right now isn't coming from imagination. It's coming from inside cosmology itself. The people who built our modern understanding of the universe are now looking at new data and realizing something isn't fitting anymore. The numbers don't line up. The universe appears to be expanding too fast when measured one way, and too slowly when measured another. Galaxies are showing up earlier than expected, more massive than they should be, and in some cases, more organized than our models allow. The deeper we look, the harder it becomes to treat these as small, isolated problems. This is starting to feel like something bigger. A crack in the model that was supposed to explain everything. At the center of this tension is a simple number, the Hubble constant. It describes how fast the universe is expanding right now. In a solid scientific framework, different methods of measuring it should give roughly the same result. But they don't. One method looks back into the early universe using ancient light left over from when the universe was very young. That approach predicts a slower expansion rate. Another method looks at nearby stars and exploding supernovae to measure distances directly in the present universe. That gives a faster rate. The difference might seem small, but in cosmology it's huge. It means something fundamental may be off. If the expansion rate is wrong, then our estimates of the universe's age, distances between galaxies, and the timeline of cosmic history all shift. For a while, scientists hoped the problem came from measurement errors. Maybe the stars used for distance calculations were affected by dust or crowding. A more powerful telescope was expected to fix that. But when newer, sharper observations came in, they didn't remove the discrepancy. They confirmed it. That's when the tone changed. If the measurements are holding up, then the model itself might be incomplete. And the tension doesn't stop there. When we look deep into the universe, we're seeing galaxies that seem too big, too bright, and too evolved for their age. These were supposed to be early, immature systems. Instead, some look like they've already grown up far too quickly. Even after correcting for effects that can make galaxies appear brighter than they really are, there still seem to be more massive early galaxies than expected. Enough to raise serious questions. There are also signs of structure appearing earlier than it should. Patterns and shapes that, according to current models, should have taken much longer to form. Then there's another concern. The universe might be less clumpy than predicted. Matter doesn't seem to be clustering exactly the way our models say it should. Individually, each of these issues might be manageable. But together, they start to point in the same direction. Something is missing. One possibility is that dark matter, the invisible substance that helps shape galaxies, may not behave exactly the way we think. Another idea is that some unknown form of energy influenced the early universe in ways we haven't accounted for. Or it could be something even more fundamental about how space itself works. The important thing is this: the current model of the universe still explains a lot. It's not broken. But it may not be complete. When people say, "This isn't our universe," they don't mean we're in the wrong reality. They mean the version of the universe described by our equations no longer fully matches what we observe. The map and the territory are drifting apart. And that's not failure. That's the edge of discovery. Science moves forward by finding where its models stop working perfectly. That's where new ideas begin. Moments like this don't close doors, they open them. What we're seeing now may be the beginning of a deeper understanding of the cosmos. A reminder that the universe is more complex, more subtle, and more surprising than we imagine. What if the universe we think we understand isn't the same universe we're actually observing? It sounds like a dramatic idea, But the discomfort is coming from within cosmology itself. The issue isn't imagination, it's the data. Some of the scientists who built our current picture of the cosmos are now looking at new observations and realizing that things no longer align. The numbers don't match the way they should. At the center of this tension is a single value, the Hubble constant, which describes how fast the universe is expanding right now. In a stable model, different methods of measuring this value should agree within small margins. But they don't. One approach, based on the early universe and the cosmic microwave background, suggests a slower expansion rate, around 67 km per second per megaparsec. Another method, using nearby stars and supernovae to measure distances directly, gives a faster rate, closer to 73. That gap may seem small, but in cosmology it's significant. A difference like that affects everything: the age of the universe, the timing of galaxy formation, and the overall structure of cosmic history. It's not a minor mismatch, it challenges the foundation of the model. At first, many researchers suspected measurement errors. Perhaps dust, crowding, or limitations in older telescopes were skewing the data. That's where newer, more powerful observations became crucial. The expectation was that improved clarity would resolve the discrepancy. Instead, the newer data strengthened it. More precise observations confirmed the higher expansion rate rather than correcting it. That shifted the conversation. If the measurements are solid, then the model may be incomplete. Something might be missing, an unknown factor influencing how the universe expanded, especially in its early stages. And that's not the only tension. Observations of very distant galaxies, meaning we see them as they existed early in cosmic history, have revealed systems that appear surprisingly massive, bright, and structured far earlier than expected. According to standard theory, galaxies should have taken longer to grow and organize. Yet some seem to have formed quickly and efficiently, almost too efficiently. Further analysis showed that some of these galaxies appeared brighter because of active black holes at their centers, which reduced the severity of the problem. But it didn't eliminate it. There are still more large, mature galaxies in the early universe than predicted. There are also hints that the distribution of matter across the universe might not match expectations. Some measurements suggest that matter is slightly less clumped than the current model predicts. This may sound subtle, but it points to deeper questions about how structures formed over time. All of these issues, expansion rate differences, early galaxy formation, and matter distribution, might be connected. Instead of being isolated problems, they could be signs that the underlying framework is missing something important. One possibility involves dark matter, which plays a key role in shaping cosmic structure. The standard view assumes it is cold, meaning it moves slowly and helps form galaxies in a specific way. But some observations hint that alternative forms, like warmer or wave-like dark matter, might better explain certain features. Changing this assumption would affect many aspects of cosmology, from galaxy formation to large-scale structure. None of this means that current cosmology has failed. The standard model still explains a vast range of observations with remarkable accuracy. But it may not be complete. The growing tensions suggest that refinements, or even significant revisions, could be needed. When people say, "This isn't our universe," they don't mean we're in a different reality. They mean the mathematical description we rely on is no longer perfectly matching what we observe. The map and the territory are beginning to diverge. This is not the end of understanding, it's a turning point. Scientific progress often happens when models stop fitting perfectly, forcing us to look deeper and think differently.